In this video, I want to give some examples of finite fields and illustrate the structure theorem that we proved in the last couple of videos. So here is the structure theorem for you. And as I said, this is the most important result that you need to know about finite fields. So we have proved each statement. In fact, we did not prove one of these statements. I simply said C follows from a group theory fact, which I didn't do. And E and F, I went somewhat fast. But hopefully, overall, it's clear to you. So what I want to do now in this video is to illustrate these results with some examples. Okay, we did one example. So I will actually talk about this example where we constructed a field of order 4, right? So in this example we constructed F4, which I denoted like this. So this is F4, right? So I'll just use the same slide here to illustrate this. So just to illustrate all the facts that we have proved here, it is a field of order 4. It has 4 elements and everything satisfies this polynomial. So in fact, this polynomial splits completely like this, right? So this is not surprising. Every element of F4 by this part D here is a root of x power q minus x. In this case, q is 4. So it's a root of x power 4 minus x. It has 4 distinct roots we observed in the proof. And the 4 distinct roots are these. And if you try to draw the extension diagram, it is degree 2. There is nothing in between. So the statement about subfields does not apply here. But if you take the statements about irreducible factors, we can say something interesting. This, remember, these are over F2. These of course are not over F2 because alpha is not in F2. So the irreducible factors of x power 4 minus x over F2 are the irreducible polynomials in F2 whose degree divides R. So in this case R is 2, right? So because 4 is 2 squared. Remember, P is 2 here, R is the exponent which is also 2. So we are looking for irreducible factors whose degree divides 2. There are 2 possible degrees. Right? So what are the numbers that divide 2? 1 and 2. So x power 4 minus x can be written as x, which is the degree 1 term, another degree 1 term x minus 1, and actually you have to multiply these x squared plus x plus 1, which we know is irreducible. In fact, we went modulo that polynomial, right? F was x squared plus x plus 1. Okay, so that's the irreducible factorization. Clearly, if you check this as an exercise, if you multiply x minus alpha and x minus alpha minus 1, you get x squared plus x plus 1, which is irreducible over F2x. So this is the factorization in F2x. Okay, so that is what I should say. It confirms the last part of the structure theorem. Irreducible factors are those that have degrees that divide 2 in this example. So it can't have 3, for example. There cannot be a factor of degree 3 because 3 does not divide 4 or 3 does not divide 2. Okay, so now let me do some other examples to illustrate this theorem more carefully. So more examples. So I'm going to study F8, right? This is a field of order 8. We know from the theorem that such a field exists and any 2 fields of order 8 are isomorphic. So in fact, I will write this as F2 cubed and it will contain F. It is degree 3. So it will not contain any other field in the middle because no other number divides 3 other than 1 and 3. And if you want to understand where F4 fits into this picture, you have F4 here and F8 is not comparable to this. Okay, this is 2, this is 3. There is no containment result between F4 and F8. Okay, so I'm going to do another example after discussing this where I draw this picture of subfields for a given field. So then you will understand this more. But let us think about what we have to do here, and let's try to not go through the irreducible polynomial part via that route, but use the proof of the structure theorem. So here we have in fact okay, so to actually understand the elements we need to get hold of a degree 3 irreducible polynomial in f2x. Okay, so it is very easy to check, for example, that is given by x cubed plus x plus 1. Okay, this has no root. 0 is not a root of this because 0 plus 1 is 0. 1 is not a root of this because 0 plus 1 is 1, which is not 0. 1 plus 1 is 1, which is not 0. This is irreducible, and f8 will be actually equal to f2x modulo x squared plus x plus 1. So if you, as before, declare alpha to be x bar, there will be 8 elements, remember. There will be 8 elements which correspond to how you put coefficients in front of these 3 basis elements. So I am going to just list them in some order. You will have 1, 0, 1, alpha plus 1. So I will just follow the way I have written this. Alpha squared plus 1, alpha squared plus alpha plus 1, alpha squared plus alpha. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 elements, right? These are all distinct elements. Remember, these are given by putting one of the 2 possible coefficients in front of 1. Similarly, one of the 2 possible coefficients in front of alpha, one of the 2 possible coefficients in front of alpha squared. One can check here that, alpha generates actually f8 cross. Okay, because you can check here, alpha squared is there already, alpha cubed is alpha plus 1. You can check that alpha power 4 is alpha squared plus alpha, alpha power 5 is alpha squared plus alpha plus 1, alpha power 6 is alpha squared plus 1. Okay, and alpha 7 will be 1. So f8 cross, remember, is a cyclic group. Our theorem tells us this, but you can actually verify that alpha generates f8 cross. It is order 7. Okay, so this verification I will leave this for you as an exercise. This is easy, right? We know that this is something is wrong here. It's not x squared, but I put x cubed. So we know that alpha cubed plus alpha plus 1 is 0. That means alpha cubed is minus alpha minus 1. That means it is actually equal to alpha plus 1, because minus alpha is alpha, minus 1 is 1. So using that reduction, you can write down all other things. So it is a cyclic group of order 7. Okay, so this also tells us that x power 8 minus x is actually splits completely in f8. Splits completely in f8. It's x into x minus 1 into x minus alpha into x minus alpha minus 1 and so on. So the last will be x minus alpha squared minus alpha. Right? So there will be these 8 terms. One corresponding to each of these elements, x minus 0, x minus 1, x minus alpha minus 1, x minus alpha squared and so on, all the way up to this. This is a factorization. Remember this factorization only holds in f8x, not in f2x, because remember alpha squared, all these elements are not in f2x. So how do you actually find the factorization in f2x? This is where we have to use the theorem. The structure theorem said the irreducible factors of alpha x power 8 minus x, you take q to be 8, are the irreducible polynomials in f2 whose degree divides r. Here 8 is 2 power 3, so r is 3, q is 8. Okay, so I will just write, I will erase this, but here we are looking at r equal to 3, so we are looking at irreducible polynomial whose degree divides 3. So possible degrees are 1 and 3. The only numbers that divide 3 are 1 and 3. So in fact the factorization turns out to be x times x minus 1 will always be there. That corresponds to the two factors that already exist in f2x, but the other ones will be the polynomial that we went modulo. So it will be x cubed plus x plus 1, and you can also check that it is x cubed plus x squared plus 1. Okay, so check this. This works. This is the irreducible factorization. Only irreducible factors are those of degree dividing r. So in this case r is 3. So r must divide, degree must divide 3, so that means only 1 and 3 are possible. So I'll just do one more example, a couple of more examples illustrating this. So let's look at f16. So this is degree 4 polynomial that we have to take, and this has order 4. So if you take f16, things get a little more interesting because this is f2 power 4. This does contain f2 squared, right? Because one of the statements of the structure theorem is that f, okay, so maybe I'll just refer to that. So f p power r contains f p power k if and only if k divides r. So in our situation, f2 power 4 contains f2 power 2, but it does not contain f2 power 3. Okay, so this is a field above this is a field of this, but there is a tower like this. Okay, so in this, if you take x power 16 minus x, how do you factor this? Here possible degrees are, because here r equal to, so 16 equals 2 power 4, so r equal to 4, right? So possible degrees are things that divide 4, that means 1, 2, 4, and a simple calculation will tell you that the factorization we are looking for is there will be degree 2 terms, degree 1 polynomials, there is a degree 2 polynomial. Remember that captures f4. The roots of these, so far what I have written, the degree 4 part, roots here of this form the f4 that's contained in f16. But then you will have some other terms, and those other terms will be all degree 4. Because it cannot be degree 3, there is only degree 1, degree 2, so the remaining things are all degree 4. And I have computed this, this is what it looks like. So I will write it down and you can check this, x4 x cube plus 1, x4 plus x plus 1. Okay, so this is the factorization. Again illustrating the last part of the structure theorem. Okay, so now one more example. Let's look at f9. So here q is 9, that means 9 is 3 squared, so r is 2 and p is 3. So f9 is a degree 2 extension of f3. So also I should finish this, put numbers here. So this is a degree 3 extension f8 of f2, this is a degree 2 extension, this is another degree 2 extension, and this is a degree 4 extension, as we know, also confirmed by the multiplicativity of degrees. Okay, so here we can actually write down all the elements, and if you look at one, so f9 in fact can be computed as f3x. Here we have to take start with f3, and x cubed plus x plus 1 is the polynomial which is irreducible. See, even for a degree 3 polynomial, this trick of finding roots will tell us it's irreducible or not, because if a degree 3 polynomial is not irreducible, it factors as a product of two smaller degree polynomials. One of them must be degree 1 at least, because you cannot have all degree 2s, right? Because then it will add up to at least 4. So a polynomial of degree 3 is irreducible if it has no roots, and F3 has 3 elements 0, 1 and 2. 0 cube plus 0 plus 1 is not 0, 1 cube plus 1 plus 1 is actually 0, so I should take here 2, right? Because sorry, actually I'm sorry, I have to take x squared plus 1, maybe I should take this. That's one possibility. I wrote it wrongly. X squared plus 1 I claim is a irreducible polynomial because yes. So what are the roots? Possible roots: 0 squared plus 1 is 1, which is not 0. 1 squared plus 1 is 2, which is non-zero. And if you do 2 squared, 2 is minus 1 actually. So 2 squared plus 1 is 4 plus 1, which is 5, which is 2, which is non-zero. So this will, for example, give you a polynomial which is irreducible, and you can factor that and write that as a field of degree order 9, and its elements can be written as 0, 1, 2, alpha. Here 1 comma alpha will be basis, so it will be alpha square will be 2, so 1 plus alpha, 2 plus alpha, and so on. So I'll not write all the 9 elements, there will be 9 elements. The interesting thing is how to factor x power 9 minus x. X power 9 minus x in F9 will be x, x minus 1, x minus 2, and so on, x minus alpha, x minus 1 minus alpha, and so on in F9x, because elements of F9 are roots of x power 9 minus x. There are 9 of them, so it's completely splits, whereas this is not the factorization in, this is not valid in F3x. Okay, so what is the correct factorization? Here remember, the irreducible factors must have degrees dividing r, which is 2. So here possible degrees are 1 and 2. So we have x, x minus 1, x minus 2. These are linear factors coming from F3 itself, and the remaining things are all degree 1. One of them is the one we started with. There will be another, remaining ones are degree 2. It will be x squared plus x plus 2 and x squared plus 2x plus 2. One can check that these are all irreducible. So this is the irreducible factorization in F3x. The only possible irreducible factors of x power 9 minus x have degree 3. We know that because by the structure theorem, the factors of x power 9 minus x have degrees which divide 2 in this situation. So there cannot in particular be, so as a separate consequence, there can't be a degree 4 factor, irreducible factor, or degree greater than or equal to 3 factor of x power 9, x power x minus 9 in F3x. This is another way of saying this. Every factor is either degree 1 or 2. So this is the factorization. So this illustrates mainly the last part of the structure theorem, which I proved maybe somewhat quickly, and I hope the examples illustrated that statement. Now I'm going to do one more example to illustrate the subfields of a given finite field. So tower of fields, or it's called lattice of subfields. Okay, so let me illustrate this by drawing some lattices. So for example, if you take f 2 power 18, okay, so this is a field containing 2 power 18 elements, right? This is a large, huge number, right? It's a very big field. Draw the lattice of subfields of this. So I'm going to appeal to the structure theorem, the part of the structure theorem which said if a field of p power r contains a field of p power k, remember p must be same. Clearly you can't contain a different p because they're all above z mod p z. So p must be same, but exponents also have a relation. R must be divisible by k. So here we are taking 2 power 18. So we are looking for 2 power k where k divides 18. So what are the numbers that divide 18? So I'm going to draw here. So let me start with this. So f 2 power 18. At the bottom we have to have f2. But what are the divisors of 18? So let me write that here. We are interested in divisors of, remember the divisors of the exponent are what we are looking for. Divisors of 18 are 1, 2, 3, 9, 6, 9, 18. Right? So all fields f2 power 1, f2 power 2, f2 power 3, f2 power 6, f2 power 9, f2 power 18 are going to appear in this lattice. So let's do f2 power 9 here. Because 9 divides 18, this is a valid subfield of that. Whereas if you do f2 power 6, that's a valid subfield, but 9 and 6 are not comparable because 6 does not divide 9. On the other hand, 3 divides both 9 and 6, so that's f2 cubed will be in both of them. Whereas f2 squared will be in this but not in this, hence not in this. Right? It will be in f2 power 18. These are the fields that we considered already, f8, f4. And of course, these are both in f2. So this is the lattice of fields, right? 2 power 18. 9, 6, 3, 2, 2. Okay. What about, I will look at some other examples. 3 power 12. So what are the divisors of 12? Divisors of 12 are 1, 2, 3, 4, 6 and 12. Okay. So you have f 3 power 6 here. Also 3 squared will be contained here. Also, so let me write like this. 3 cubed will be contained here because 3 divides 6. And there will be another subfield 3 squared. 2 divides 6, 3 divides 6, but 2 and 3 are not comparable. On the other hand, you will have 4 here. And 4 will be contained in this, but this side of the lattice is not comparable to this. And at the bottom we have f3. Right? So I hope this makes sense to you. So 3 power 3 is contained in 3 power 6, but 3 power 3 is not contained in 3 power 4. 3 squared is contained in 3 power 6 as well as 3 power 4, but not in 3 power 3. And everything is above 12. And I'm just randomly choosing primes here. If 2 is replaced by any other prime, the lattice does not change because only the exponents are relevant here. The prime itself is not relevant. So for example, if you take f 5 power 10, 10 has factors 1, 2, 5 and 10. So here I get f5 power 5, f5 power 2, and there is no other factor, so this is just f5. So important remark, in each of the above, if we replace the prime, if we change the prime, the lattice does not change. Only the exponent is relevant. So what I am saying is that here 18 is the relevant number. So if you instead of 2 you have 3 or any other prime, 13 power 18, everything will go through. It will be f13 power 9 here. Here it will be f13 power 6, here it will be f13 power 3, here it will be f13 power 2, and here it will be f13. What the prime is irrelevant, because the crucial statement of, as long as of course you keep the prime same, if you can't put 13 here and 2 here, prime is the same. Whereas if you change 18, the whole thing changes. In the crucial structure theorem statement, a field of order p power r contains a field of p power k if and only if k divides r. As long as p is the same, r and k are the only relevant numbers. So here we can, without changing anything, replace 2 by a different prime. Here replace 3 by a different prime, replace 5 by a different prime. The exponent is the crucial thing to determine completely the lattice. Okay, so this is some of the examples I wanted to do to illustrate the structure theorem, especially the last two parts, which were important in understanding the lattice of subfields or the irreducible factorization of the polynomial x power q minus x. So I am going to stop the video here, and this completes the course. I will just do 1 or 2 more videos solving some exercises on fields, but the main part of the course stops here. In this course we have studied rings and fields. This is really a it's supposed to be a first course. We covered some standard topics that are covered in a first course. It goes without saying that there are lots of topics that I have not touched on in ring theory as well as in field theory. For example, I didn't talk about primitive extensions, Galois theory and so on. So these are all covered in a second course in field theory. In rings also we didn't talk about factorization of rings and Euclidean domains and so on. These are some of the topics that we have not covered. But my goal in this course, in this 8-week course, was just to give you an introduction to the theory of rings and fields and illustrate how one solves problems in these topics. So I hope you enjoyed the course, and you should solve all the exercises that I have been giving in the class and ask questions in the discussion forum to understand the material better, and carefully watch the videos if you have any questions. And remember, again I will stress this fact, this is only a first course. If you really want to understand ring theory and field theory better, there are courses that you can take as follow-ups to this. Let me stop the video here. In this video we did examples to illustrate the structure theorem for finite fields, and this completes the main part of the course. In the next 1 or 2 videos we will do some exercises. Thank you.